There's a photograph taken in 2019. It shows something 55 million light years away. Something we call a black hole. We celebrated. We said we'd finally seen one. But hear what nobody mentioned. We didn't photograph a black hole. We photographed the absence of light around something we cannot see. Something we cannot touch. Something that, when you ask what it actually is, physics goes silent. You think you know what a black hole is. A star that collapsed. Gravity so extreme that nothing escapes. Not even light. That's the story in textbooks, in documentaries, on science Twitter. It's treated as settled fact. Black holes are exotic, yes. Dangerous, yes. But understood. We have equations for them. Carl Schwarzschild derived the first solution to Einstein's field equations in 1916, while serving in World War I, suffering from an autoimmune disease that would kill him months later. His mathematics described a perfectly spherical mass, compressed to a point. We call it a Schwarzschild black hole. Since then, physicists have built entire careers on black holes. Roy Kerr described rotating ones in 1963. Roger Penrose proved they must contain singularities, work that won him the Nobel Prize in 2020. Kip Thorne spent decades calculating what happens near them. We've simulated millions of them. We've detected their collisions through gravitational waves. LIGO heard two black holes merge in 2015. The mathematics is pristine. The models are consistent. The predictions match observation. For decades, physics spoke about black holes with absolute confidence. We could calculate them, predict them, even photograph them. We believed they were dangerous, but understood. That belief will not survive the next 15 minutes. Because the moment you try to define a black hole precisely, language starts to fail. Where exactly is it? Here, what should be a simple question. Point to a black hole. Not the accretion disk. Not the gravitational effects. The hole itself. You can't. Because the event horizon isn't a surface. It's the last moment you could have changed your mind. The singularity isn't a place. It's a timestamp you cannot avoid. Ask a physicist to define a black hole precisely, and watch them give you equations instead of answers. The mathematics describes something unsettling. A boundary where nothing special happens. And yet everything changes. After that point, later stops meaning what it used to mean. Inside a black hole, space and time exchange roles. Let me say that again, because it's not a metaphor. Inside a black hole, space and time literally swap their mathematical properties. Outside, you can move through space, left, right, forward, back. You can change direction. You can stop. But time flows in one direction, always forward. You cannot turn around in time. Inside a black hole, it reverses. The singularity, that infinitely dense point at the center, isn't ahead of you in space. It's ahead of you in time. You are not moving through space toward it. You are moving through time toward it. Just as you cannot stop aging outside a black hole. You cannot stop approaching the singularity inside one. It is as inevitable as next Tuesday. The singularity is your future, not a location you're traveling to. A moment you will experience. And there is no experiment, no maneuver, no clever trick that prevents it. This isn't speculation. This comes directly from the Schwarzschild metric, the most basic black hole solution. The mathematics is clear. What it means is not. Because if the singularity is a moment in time, what does it mean to say the center of a black hole? Centers are spatial concepts. But we've just established that inside a black hole, the radial coordinate behaves like time. So we use spatial language for something that is no longer spatial. This is the first crack, and it only gets worse. Here's the confession physics tried to bury. General relativity does not just predict black holes. It predicts its own breakdown. At the singularity, the equations don't crash. They don't refuse to compute. They keep running and produce infinity. Not very large numbers. Not approaching infinite. Actual infinity. In physics, infinity isn't an answer. It's a surrender. A white flag. It means I can no longer describe reality. When your theory produces infinities, it's not revealing something profound about the universe. It's revealing something broken about the theory. Infinities don't appear in nature. They appear in mathematics that has exceeded its domain of validity. When you divide by zero, you don't discover that something is infinitely large. You discover that you've asked a question your framework cannot answer. The singularity is general relativity dividing by zero. And yet, the equations keep running. They produce outputs, predictions, numbers. They just stop meaning anything. Think about that. Our best theory of gravity continues calculating. Something it cannot interpret. The math survives. Meaning does not. We pretend otherwise. We say quantum gravity will fix it. We say when we unify quantum mechanics and general relativity, the singularity will be resolved. But quantum gravity doesn't exist yet. We don't have it. We don't even know if it's possible. So inside a black hole, right now, in every black hole that exists, our physics works and doesn't work at the same time. Let me be clear about what this means. We can calculate trajectories inside a black hole. We can predict how fast you would fall. We can tell you how long, measured by your own clock, until you hit the singularity. For a solar mass black hole, microseconds. For a supermassive black hole like the one at the center of our galaxy, hours. The math works. But ask what you'd see. Ask what the singularity is. Ask what happens at infinite density. And physics has no answer. Not we haven't figured it out yet. Not the calculation is too hard. There is no coherent answer the theory can provide. Because the theory has stopped describing reality. It's computing, but not explaining. It's like a calculator that keeps displaying numbers after you've divided by zero. The screen shows error, but the calculator keeps running anyway. And the strangest part, we've accepted this. Physicists know general relativity breaks down at the singularity. They've known for decades, and they keep using it. Because outside the singularity, it works flawlessly. It predicts orbits, gravitational waves, the bending of light. It's been tested thousands of times. It has never failed. Until it does. At the one place it promised to take us. And then there's the problem physics try to hide. The one that breaks everything. Information disappears. In quantum mechanics, the other pillar of modern physics, information is sacred. It cannot be created. It cannot be destroyed, only transformed. This isn't a suggestion. It's a fundamental law. Burn a book, and the information isn't destroyed. It's encoded in the smoke, the ash, the radiation. Scrambled beyond recognition, yes, but preserved. Always preserved. Except in black holes. Stephen Hawking discovered black holes radiate. They evaporate. Eventually, they disappear completely. Here's the problem. Information that fell in, gone. Quantum mechanics says information is never destroyed. General relativity says it was. Both theories tested to absurd precision. Both can't be right. Hawking spent 30 years trying to fix it. In 2004, he conceded. Said information must survive somehow. But he couldn't explain how. Neither can anyone else. 40 years, thousands of papers. No resolution. This isn't a puzzle waiting to be solved. It's a signal that our understanding is incomplete at a foundational level. Here is the moment physics goes silent. Inside a black hole, laws still exist. Equations still run. Mathematics still produces outputs. But explanation ends. Roger Penrose called singularities cosmic censorship, because the universe seems to hide them behind event horizons. We cannot see them. We cannot probe them. We cannot send a signal out from inside. It's as if reality itself has quarantined the breakdown. But it goes deeper than that, because it's not just that we can't measure what happens inside. It's that the concept of measurement may no longer apply. Causality dissolves. Time stops being navigable. Space stops being spatial. Coordinates become meaningless. There is no experiment you can even imagine that tells you what actually happens. Not because of practical limitations, not because of engineering challenges, but because the framework for asking questions has collapsed. A black hole is not just an object we cannot see. It is a region of reality, where explanation itself breaks down, where the tools we use to make sense of the universe, mathematics, causality, measurement, continue operating, but stop connecting to meaning. Physics still speaks. It just no longer understands what it's saying. And the most haunting part, there's no reason to think we'll ever know. Not we'll figure it out eventually. Not with better technology. Because the barrier isn't technological. It's epistemic. There is no information channel from inside a black hole to outside. Even in principle. Even with infinite time and infinite resources. We are not waiting for a better telescope. We are facing a structural limit on what can be known. And physics, for once, has admitted defeat. So what is a black hole? The honest answer, we don't know. Not because they're far away. Not because we lack data. But because the question may no longer have a coherent answer. John Wheeler, the physicist who coined the term black hole in 1967, spent his final years obsessed with this problem. He called black holes the most perfect macroscopic objects in the universe. Perfect mathematically. But he also said they were the place where all of our usual ideas about space and time simply fail. He died in 2008. The problem remains. Black holes are not monsters of gravity. They are wounds in explanation, places where reality refuses to be translated into meaning, where the universe computes but does not reveal, where laws continue but understanding ends, and we are left standing outside, watching equations march forward into a region we cannot follow, not with spacecraft, not with mathematics, not even with imagination. Because inside a black hole, inside may no longer mean anything. We opened with confidence. We close with confession. Physics has given us the most accurate description of reality ever conceived. It has predicted particles before we found them. It has revealed forces we cannot see. It has taken us to the edge of the observable universe. But at the center of a black hole, at the place where all that power converges, it stops, not because it's broken, but because reality itself may have edges, where questions end, and physics, humbled quiet, finally admits, we don't know.